Welcome to the third presentation in Unit 9 entitled So You're Telling Me There's a Chance. The learning goals for this presentation are that you be able to determine the solubility of a substance based on the KSP, and that you be able to determine the concentration of a substance based on the absorption of light. So, things that you should already know. You should already know that substances can be classified as soluble or insoluble, and that represents a degree of solubility. So is it a lot soluble? Is it a little bit soluble? Ionic substances are generally soluble in water, and that nonpolar substances are generally insoluble in water. So here's what we learned in the lab. The solubility of a substance depends on the actual ions that are present. Things like lead tend to, for the most part, be insoluble. Not all ionic compounds are soluble, but all alkali metals, which remember are group 1, are soluble. So, ionic solutes. The first thing that we should realize is that whenever you have a solute, you can write what's called a dissociation expression. And this is what's called a dissociation expression. You see what I have is solid salt, and what it's doing is it's reacting, or when I put it in water, it turns into Na plus, which is the cation, and Cl minus, which is the anion, and they change their state to be aqueous. That aqueous means that they're dissolved. So you can do the same thing for sodium sulfate that you see here, except the difference is that there are now two sodiums and then just one sulfate. So this is what's called a dissociation expression. This dissociation expression is showing us what happens when you put an ionic substance in water. Now, this dissociation leads us to classify ionic substances as electrolytes. Electrolytes are called electrolytes because they dissociate, and that dissociation allows them to conduct electricity. So if you were to run an electrical current, the fact that you have ions here will allow electricity to flow freely through that particular substance, whereas with traditional water, they would not. Now, what we can do now is we can generate something called an equilibrium constant expression. So it says chemical reactions generally move in both directions, and so what we do is we create what's called an equilibrium expression to say, hey, this is how much there is when they're in balance. Because remember, equilibrium means that they're in balance. So whenever we look at soluble or insoluble or somewhere in between, we say, okay, the substances are insoluble, will still dissolve slightly, like a very, very small, like 10 to the minus 12th, but they still do dissolve. Are they really insoluble? And the answer is yes. The soluble, insoluble is a degree of solubility, not an absolute. So we generate what's called the equilibrium constant expression. This is a general chemistry equation because you will see K several times throughout your chemistry career. If you have a general equation, so you have like AA, BB, CC, DD, and these numbers represent the coefficients. These are the coefficients, and then these right here represent the substances. Okay, so an example of this would be 2HCl plus NaOH. Well, we can't do that. We're going to have to say CaOH2 goes to, and then there would be products on the other side. This represents the lowercase a. This is the capital A. This is the lowercase a or b. This is the capital B. So these right here represents a general equilibrium expression where you have this equilibrium constant K, and it equals AA, BB, CC, DD. So, the solubility product constant is a more specific version of K because it's looking only at the solubility of a particular substance. So, whenever you write one of these KSP expressions, it is specifically saying, okay, I'm looking at KSP, which means I'm only looking at as NaCl goes to Na plus Cl minus. Okay. It is used to calculate the amount of material that's actually dissolved, because once you calculate this value, it'll show you how much is dissolved and how much is at the bottom. Now, one key thing is that only aqueous and gas substances are uses, which means that if it's solid, if you have a solid like NaCl, that is not included in the K expression. If you have a liquid like water, it is not included in the K expression, only aqueous and gases. Generally speaking, you can look up the KSP. So you would say, okay, I'm looking at silver chromate, and I'd look up the dissociation of silver chromate, and I'd go, wow, it's 9 times 10 to the minus 12. That must not be very soluble at all. Or I can look at cadmium sulfide and go, wow, that's very insoluble. So you can take a look at these things and use these KSPs to determine solubility. Okay, So this one says, what states of matter are included in the KSP expression? And remember, the only ones that we're going to include are gas, and then the one that's not here, but is shown right here, which is aqueous. Those are the only two that we're going to use, gas and aqueous. Next, it says write a KSP expression for the ionization of lithium phosphate in solution. So I would write a dissociation expression. I would say, okay, lithium phosphate is going to go to lithium plus phosphate. Now I would need to put a 3 right here to balance my chemical equation. And I would say, okay, so for this, I would have there to be, my A would be 1, my capital A would be this. Now lithium phosphate is a solid crystal, so because of that it's not going to be included in the KSP expression at all. So instead I would write a KSP expression. I would say KSP is equal to the concentration of lithium times the concentration of phosphate. And then now I need to put a 3 right here for lithium. The reason why is lithium has a coefficient of 3. Now I could put a 1 for the coefficient of phosphate, but generally speaking you don't put the coefficient of 1 there. You just assume that it is 1 if there's nothing listed there. So this is what we would call the KSP expression. It would be lithium to the third times phosphate. Next it says 200 grams of silver iodide and 200 grams of silver 1 chloride are added to separate 1 liter volumetric flasks, and then water is added to the mark. What is the concentration of silver ions in each? So if you were to look at this, the first thing we need to do is we need to write dissociation expressions. We have silver iodide and silver chloride, so we'd say Ag, I, and AgCl. They both disassociate. So we say Ag plus and we say Cl minus. Okay, are added to separate 1 liter volumetric flasks, and then water is added to the mark. What is the concentration of silver ions in each solution? So these are separate calculations. We're just using them for comparison's sake. So we say Ag plus and I minus. Okay, so now what I need to do is I write a KSP expression. And so when you write your KSP expression, you would say KSP is equal to Ag, I, and KSP is equal to Ag, Cl. And at this point, you would realize that you would have a difficult time solving this equation unless you knew the KSP values. Now, the KSP values you could look up on the chart that was on the screen earlier, or we'll go ahead and tell you that the KSP for silver iodide is 1.5 times 10 to the minus 16th. The KSP for silver chloride is 1.56 times 10 to the minus 10th. Now, we know this dissociation is going to occur, but the question that I have for you is how much? And the answer is we don't know. So what we do is we say, okay, if I don't know how much dissociation occurs, I'm going to represent that by X. So I'm going to say that there's X silvers. Well, if there's X silvers, for every silver there is, there's going to be I as well. So because of that, I have values for X and I. And now this is a really easy expression to solve. I have 1.5 times 10 to the minus 16th is equal to x squared. So I can easily solve for x squared by taking the square root of both sides. For 1.56 times 10 to the minus 10th, I can easily say, okay, for every one of these, there's one of those, so you get x squared as well. Take the square root of both sides, and that will tell you the solubility of each. Now, if you were to look at the solubility of silver iodide, it's 1.22 times 10 to the minus 8th molarity, okay, which is a really, really small value. But if you were to look at the other one, silver chloride, it's 1.25 times 10 to the minus 5th molarity. Now that may not seem like a huge difference because they're both very small, but you can get about 1,000 times more silver chloride in solution than you can silver iodide. All right, now it says measuring the concentration. Whenever you're measuring the concentration, it's easily to do it qualitatively if you can look at the color of the solution. You can clearly say that this one is much more concentrated than this one, and you would say that this one is considered to be the dilute solution. Okay, but it is difficult to measure the concentration quantitatively. You can look at it and say this one's more concentrated, this one's more dilute, but how much more? Is it one time? Is it two times? Is it three times? And so it's really difficult to do. Instead, what we do is we use something that we learned earlier this year. The fact that atoms will only interact with certain colors of light. In fact, whenever you have an atom, for this thing to absorb light, it has to absorb the exact frequency that will allow the electron to transition to a higher level. And we studied earlier this year that that energy is equal to hf, which we said h was Planck's constant, and we said that f was the frequency. And that these things have to be very, very specific. Well, it turns out that if you can shine light on a sample, you can measure the missing light. And whenever you measure missing light, that missing light is related to the concentration. So what you do is you say white light consists of all colors of the spectrum, Roy G. Biv, red, orange, yellow, green, blue, violet. So because an object is a certain color, it absorbs certain colors and it allows others to bounce off. So whenever it absorbs certain colors, the fact that it absorbs those colors allows you to use the absorption to look at concentration. Okay, now a spectrometer is a device that allows you to select a wavelength and measure how much light is being absorbed. If you were to look at this particular example that we did, this solution is blue-green. So if I were to try and examine it with blue-green light, I wouldn't have very good luck because blue-green light is not absorbed by the solution. Instead, what I would do is I would have to pick one of the other colors, like red or yellow or orange. If I were to use red or orange or yellow, I can look and I can say, well, here's my wavelength of light. What color, what's being absorbed, how much light is there actually going into the sample, and how much light is coming out, and that'll tell me approximately how much of a solute there is. This is actually a very, very, very accurate method. Now, the absorption of light is going to depend on a couple of factors. It's going to depend, number one, on the absorptivity. The absorptivity is generally referred to as a lowercase a. So different substances will absorb different wavelengths based on their bonds, because remember the whole electron configuration. Remember, it's got to be able to bump up to the next level. So it's got to be able to go from here to here. If it can't do that, then it's not going to absorb that light. This substance right here is called crystal violet. It does not absorb things in the red sample. Okay? It does absorb things in the yellow sample. So if I use yellow light, it'll bump it up to the next level. But if I use red or purple, it doesn't do anything. So because of this, you have to be real careful about what wavelength you use. But also, the absorptivity allows us to say different substances will absorb different amounts of light depending on the color. So this right here is generally a constant for what you're looking at. It's not something that you're going to be able to determine. Okay, next is path length. Whenever you increase the path length the light has to travel through, you're going to increase the absorption. For example, if I have light that comes through, it's very unlikely that it's going to hit one of these molecules. But if I have a larger path length, it's more likely that it's going to interact with one of these molecules at some point. So whenever you also increases the error due to scattering. So generally speaking, you want to keep the path length relatively small so that you're not getting different values based on scattering or random chance. Now, almost every spectrometer that's used tends to have a 1 centimeter path length. The only reason why you would use a longer path length is if you were looking at something very, very, very dilute. Next, you have the concentration. Whenever you increase the concentration, you also increase the absorption. So whenever you look at something like this, it's very unlikely that it's going to interact with a particle, but here it's much more likely that it's going to interact with a particle. So, which color light would be absorbed by a blue solution? So the first thing that you can do is you can eliminate blue. You don't want to use blue when absorbing blue because blue is not absorbed by blue. So instead, what you want to do is you want to use the opposite color as best you can. The best color to absorb blue or to analyze blue with is red. All red is absorbed. Okay? The blue is not absorbed. So because of that, you can't use it. You could also use orange or yellow or something along those lines, but the furthest you can get away from it, red is going to be the best color to examine a blue solution with. Now we get to what's called the Beer-Lambert Law. The Beer-Lambert Law is A, which stands for absorbance, is equal to ABC. It's probably the easiest formula you have to memorize all year, right? A equals ABC. This lowercase a is a constant that depends on the substance that you're analyzing. Not only the substance, but the wavelength as well. So that's something you would look up from a table that would be provided to you, those sorts of things. B is the path length. Like we said, the path length is in centimeters, and it's generally 1 centimeter. And then the C term is the concentration. So that's generally expressed in molarity. So you see the molar absorptivity is molarity in centimeters to the minus 1. You have molarity in centimeters. There are no units for absorbance. Absorbance is a ratio. So if it's saying something like, I put out 100 light and now there's only 40. So the absorbance is 0.4. It's a ratio. Because of that, there are no units. It is measured with a light sensor, though. So here you have a question that says a 1 times 10 to the minus 6 molar solution of lead nitrate shows the following absorptions are at different wavelengths. The spectrometer uses a 2 centimeter length path. Determine the molar absorptivity at 635 nanometers. So the first thing you need to be able to do is you need to be able to identify which one is 635 nanometers. 635 nanometers is red. So now that you know that it's red, now you know which spectrum or which part of the spectrum we're going to analyze. So we would use red light, and so since we're going to use red light, we know that the absorbance or A value is 0.35. We know the concentration of the sample, which is C, and we know the path length, which is our B term. Using that, we can actually calculate the A term. Now, generally in the lab, you're not going to calculate the lowercase a. Those are constants, but at some point these A values had to be determined. So this is one way that they did it. So you would say, okay, A equals A, B, C, or 0.35 is equal to lowercase a times 2 times 1 times 10 to the minus 6, which is a very, very small concentration. Whenever you calculate this out, you end up getting an absorptivity, which is the lowercase a, of 175,000, and then it's molarity centimeter to the minus 1. Next, it says a calibration curve is generated to determine the concentration of red dye in fierce red Gatorade. A student generates the calibration curve below. What is the concentration of red dye if the fierce Gatorade has an absorbance of 0.37 at 430 nanometers? So the first thing you realize is that our Y value is our absorbance, and our X value is our concentration. And if you look, our concentration is actually in milligrams per liter, which is fine for this particular question. So we would say absorbance is equal to 0.0419 times the concentration plus the 0.0088. This right here is a standardized curve. Built into the slope are the absorptivity and the path length together because it's consistent for this entire investigation. So I can just use this equation. I can say I have an absorbance of 0.37. I have 0.0419. The concentration that I have is what I'm trying to solve for. And then finally you have this plus 0.088. 0088. Left out a 0. Okay, so now when you subtract and you end up solving, so you'd subtract both sides by 0.0888 and then divide by 0.0419. And when you do that, you get a value of about 8.6 milligrams per liter, which is a pretty small concentration. The last example we have is Mastery B4. It says a student is investigating the amount of blue dye in a new sports drink. The FDA requires that the food dye be kept to the minimum value necessary to achieve effect. And that's a true statement, which is kind of vague and ambiguous. The student sets the colorimeter at 430 nanometers and records the absorbance. The absorbance is so low, the student reports the amount of the dye as negligible. What needs to be done before this appears on a nutritional label? And the answer is you need to use a different wavelength. Okay, the reason why is 430 nanometers approximates blue. Remember, you have to choose the wavelength that is most different from the color that you see. So you have to choose a different wavelength like red to examine this. If with red and blue, and then I would try one more, it still shows up as negligible, then you can repeat or then the experiment has been repeated and you can still report it as negligible. But you have to use the right procedure, the right wavelength whenever you're examining these things.